For centuries, people have used the free power of the wind to help do their work. Sometimes these machines have pumped water. Elsewhere, and at other times, people use the wind to grind grain, to saw wood, to generate electricity, to even churn butter. Today, some engineers and economists predict that in the near future, increasing amounts of our electrical power will come from the wind. Thousands of wind machines like this one for decades pumped groundwater for humans and their animals to drink. Now abandoned and rusted, it once spun in the breeze above the sparkling water it elevated. Throughout arid and semi-arid parts of the world, windmills provided indispensable service, for in many areas muscle power would otherwise have had to operate the pumps. In many places, wind pumps became commonplace. The spinning wheels marked the places of human activity. An African company once declared, "Wherever you go, you see them, and whenever you see them, they go."
There's nothing that tastes so good as water that a windmill has just pumped from down in the earth. But how does a windmill do this? It's not magic, it's just basic physics. When the wind strikes the angle blades of the wheel, it causes it to spin around like a pinwheel. Ironwork at the top of the mill converts the rotary motion of the wheel into an up and down reciprocating pump stroke. You can see what I mean. The pump rod consists of several links, each one attached to the other. This rod carries the reciprocating motion all the way underground to where water is found. There, below the level of the water, it actuates a pump like this one. We call it a pumping cylinder because of its cylindrical shape. Inside the cylinder are two valves. As the pump rod moves up and down, one valve opens as the other valve closes. Through this combination of actions, the pump actually pushes water up the pipe to the surface where people can use it. Let's take an imaginary trip underground to see how this action takes place. Here in the depths of the water table, the windmill is operating the pump. Watch and listen to the check valves as they open and close. The water is lifted up the drop pipe where it flows into a stock tank. In order for all this to take place, we first have to have a well.
Here comes a driller to sink a well. He's using a rotary rig on which a rotating bit actually grinds a hole into the ground. In the process, it brings to the surface all of the rocks and soil it excavates. People have been using machines to drill wells since the middle of the 19th century. Drillers used percussion rigs which raised and dropped a heavy drill bit into the ground, pounding the rock into small pieces. Water was added to help remove the fragments. Then the hole was lined with iron pipe. In areas where the water table was very shallow, some people could dig wells by hand with picks and shovels, although it was very hard work. About a century ago, people learned that they could drill wells using a rotating pipe that had been fitted with teeth to grind holes into the ground. A modern drilling machine uses carbide or diamond face bits to do the grinding. Water from a tank on the truck is used to flush the hole, which brings to the surface all the ground-up earth and rock. When the hole has been drilled to the proper depth, it is lined with casing pipe to prevent the sides from caving in. At the very bottom, perforated plastic pipe is used, which allows groundwater to enter the well. Sand is poured to fill the area between the casing and the drilled soil. As it falls in and around the pipe, it forces water to surge out of the well. Air is injected to clean the well of any remaining drilling fragments. Once the drilling is complete, the well is measured for its depth. Then the windmill comes to pump its water.
Most people are familiar with windmills like these, but these are just the ones that people see most often in America. Our own history of windmills traces its roots back to the Old World, where historians still debate the origins of wind power technology, but no one can really prove where humans first used the renewable power in the wind to do work.
Many historians subscribe to the theory that the Crusaders brought back to Europe the windmill technology they had seen in the Middle East during the 12th and 13th centuries. There they had observed the Persian windmills. In more ancient times, people in Persia had developed wind machines adapted to their land, where the wind blows from one direction for weeks at a time. Inside squarish mud brick towers, they installed vertical wooden spindles fitted with long reed blades. As the wind entered the opening on one side of the mud brick tower, it spun the bladed vertical wooden shafts and then exited. The shafts extended downward into work areas where they turned grindstones or simple pumps. People made everything on these wind machines by hand. The vertical spindles and the braces at their tops were cut from tree trunks, brought in from long distance. They made the blades from reeds sewn together. Simple though they were, these wind machines could do the work of dozens of people grinding grain by hand or manually lifting irrigation water. If the Crusaders saw wind machines like these, they realized how much work they could do and brought the concept of wind power technology back home to Europe. Whether or not they originated in the Middle East, windmills grew popular in Britain and Europe in the centuries that followed the 1200s. These European windmills took two forms. The earlier pattern was the post windmill, named for a central wooden post cut from a tree trunk around which the entire structure rotated to face the wind. The other style of windmill was the smock mill. It was a stationary masonry or wooden tower fitted with a top that could turn to face different wind directions. Let's look more carefully at how they worked.
The structure of a post mill sits atop its wooden post so that it can turn to face the wind. Once the wheel starts turning, the wooden teeth mesh with those in a pinion at the top of a vertical shaft. Connections turn the grindstones, converting grain into more usable flour or meal. Millers control the speed of the machinery by adjusting how squarely the mill faces the wind and by changing the amount of canvas that they have stretched on the lattice-like blades. The smock mill has a tower-like structure that is rigid and does not turn. Instead, the cap on the top of the mill rotates so that the miller can direct the blades into the wind.
Immigrants from Europe brought windmill technology to the New World. All along the Atlantic coast and then inland, they built windmills like the ones they had known at home. In the United States, these substantial wind machines most often found use grinding grain. Some of them remained in use into the early 20th century. As settlers moved westward onto the plains and prairies, they encountered new areas which lacked flowing streams or lakes. For the farmers, the situation was just as serious. Unless they were so fortunate as to live on a stream or spring, they had to haul all their water for both human and animal use. They all hoped that someone might find a solution to their water problems. No one expected the answer to come from well-watered New England. This man, Daniel Halliday, invented the first commercially successful self-governing windmill in 1854. A pump repairman asked Halliday if he could devise a wind machine that would pump water or grind grain without constant attention from an operator. Halliday did so, creating the wind machine that became known as the Halliday Standard. Soon, Halliday's invention changed the paddle-shaped blades for a wheel comprised of thin wooden blades. And they gradually began to be sold throughout the eastern and midwestern states. By the 1870s, railroad companies joined farmers and ranchers in using Halliday's invention to pump water for their steam locomotives. Use of the invention spread across the plains and prairies all the way to the Pacific coast. Other windmill makers secured their own patents for wind-powered pumps, and competitors joined the field, making windmill manufacture a growth industry by the 1880s.
Halliday's 1854 invention was the pioneer, for it was the first windmill that automatically turned to face the wind and controlled its own speed of operation without direct human supervision. This was its key to success. It was self-governing. This is how it works. First of all, the tail or vane of a mill operates like a weather vane. When I release this rope, which is holding the mill out of the wind, it will automatically turn to face the wind. On the old European-style windmills, it took an operator manually to turn the mill to face the wind. Halliday's did this by itself. Halliday designed his mill to control its speed of operation so that the wheel would not tear itself apart from spinning too fast in a high wind. He placed iron weights at the end of levers attached to each section of blades in the wheel. When the wheel starts to turn too fast, these weights will tilt each section of blades out of the wind. This slows down the wheel. Then, when the wind dies down, the weighted lever at the top of the working head, through linkages, will pull those sections back to face the wind again. This system ensures that the Halliday Standard Mill operates at more or less regular rate of speed whenever it is turned on and the wind is blowing. It does not require a person either to direct it into the wind or to regulate its speed of operation. It is self-governing.
The idea of a wheel comprised of multiple sections of adjustable wooden blades caught on with a number of windmill makers after Daniel Halliday popularized it. Many of the subsequent mills did not have vanes or tails. Instead, their wheels spun on the downwind side of the towers, like this Fairbury Vaneless made in Fairbury, Nebraska. Each company painted the wooden blades and ironwork on its windmill in its own distinctive colors. Some of them added counterbalance weights and easily recognized shapes in efforts to identify their mills to customers. This practice resulted in mills having counterbalance weights shaped like animals, geometric forms, or letters of the alphabet. The Dempster Mill Manufacturing Company of Beatrice, Nebraska, for decades identified its mills from the red and white painted pattern and from the cast iron, horse-shaped counterbalance weights. Whenever anyone saw one of these mills, even from a distance, they knew that it was a Dempster product. The Outhouse Wheeler Company in Wampum, Wisconsin, advertised its hometown with big W-shaped counterbalance weights.
This crescent moon-shaped weight once regulated the speed of a windmill pumping water on the West Texas ranch of Daniel Webster Wallace. Wallace was a pioneer black rancher on the southern Great Plains. On the side it reads Eclipse, and the Eclipse windmills in the early days competed most strongly against the sectional wheel mills we've looked at so far.
Eclipse windmills were completely different in design from the sectional wheel mills. They had rigid or solid wheels, more like water pumping windmills seen in the field today. The Reverend Leonard Wheeler, in 1867, set out to develop a self-governing wind machine of his own design. He and his son developed a mill that initially used 4 paddle-shaped blades, a hinged tail assembly, and a side vane. A rigid wheel soon replaced the 4 paddles. Wheeler secured a patent on his invention, which he and his family initially produced in a simple shop. Soon, manufacture of the mill Wheeler called the Eclipse passed into other hands and sales grew, and they grew even more. The bright olive green wheels with blood red trim became commonplace, especially on the southern Great Plains. There, the Eclipse became the most common model by the end of the 1890s. Steam railroads became important buyers for Eclipse windmills as companies required clean boiler water for their steam locomotives. The company developed what it termed railroad Eclipse mills, larger diameter, heavy-duty wind machines designed to pump from greater depths or in larger volumes than possible for regular farm-sized mills. By the start of the 20th century, Eclipse windmills dotted western ranches by the thousands.
This is a big railroad-style windmill. It has a 22.5-foot diameter wheel and was made by the Axtell Company in Fort Worth around 1910. The 50-foot tall tower is made from 8x8 heavy wooden beams. On windmills this size, there's a series of cast iron balls chained together. They take the place of the moon-shaped weights used on smaller Eclipse mills. And with the side vane, which we're about to see, they help make this windmill self-governing. When the mill is turned on from the ground, you can see how the wheel swings around at a right angle to the tail. Look how the ironwork converts the spinning motion of the wheel into a reciprocating pump stroke. As the wind velocity increases, wind pressure on the side vane pushes the wheel away from the wind. This movement decreases the surface area of the wheel exposed to the wind and prevents it from turning too fast. This usually starts happening in an 18 to 20 mile per hour wind. As the wind speed decreases, the governor weights will pull the wheel back to a position perpendicular to the tail, and the wheel begins to pick up speed again.
Not all the solid wheel wooden windmills were Eclipse mills. Many different companies also made this style windmill. One of the most common of these products was the original Star, made in Kendallville, Indiana by the Flint and Walling Manufacturing Company. Sold throughout the country, the Star mills competed head-to-head with Eclipse and other mills for its share of the market. Not all windmills were made from wood. As early as the 1870s, companies like Mast, Foos and Company had begun making wind machines from iron and steel. The iron turbine holds the distinction of having been the first commercially successful all-metal windmill made in America. Produced in Ohio, they found markets throughout the United States and overseas.
A few of the iron turbine windmills survive, and this is the best preserved of them. Instead of having thin, flat wooden blades, the iron turbine had wrought iron buckets that the inventor said would be very efficient in catching the wind. On this early mill, all the working parts were cast iron or wrought iron. Like on wooden wheel mills, one revolution of the wheel provided one stroke of the pump.
One of the early steel windmills eventually dominated the American market, the Chicago-built air motor. The story of the air motor windmills begins in 1883. An old line company hired engineer Thomas O. Perry to design the most efficient possible windmill wheel. After months of work, he found that the most efficient wheel he could build consisted of a series of curved metal blades mounted on steel rims. Chicago entrepreneur Laverne W. Noyes learned of Perry's tests. Within 5 years, he had organized a new company named Air Motor to build windmills with the engineer's scientifically designed steel wheels. Through clever marketing of a quality product, Noyes built the Air Motor Company into the dominant windmill manufacturing enterprise in the United States. He made all of his pumping air motor windmills back-geared. This means that several revolutions of the wheel were required for each stroke of the pump. Consequently, air motors began pumping in lighter winds than their competitors.
This is an 1890s model pumping air motor. It shows all of the design features that made the open-geared air motor so popular.
The efficient steel wheel spins easily, providing a slow and steady pump stroke ideal for a pumping cylinder underground. All air motor windmills use Babbitt bearings, but on the early models, they had to be greased manually.
The slightly off-center wheel inclines away from increasing winds, while the tail spring pulls the wheel back more directly into the wind as the wind decreases.
This is a fine mill, and it should be no surprise that they sold by the tens of thousands.
The problem with all windmills made up to this time was that they required regular weekly lubrication. About 1912, the Elgin Wind Power and Pump Company solved the problem with its Wonder Mill. Soon other firms began introducing their own oil bath designs.
This 602 model air motor was first made in 1916. It shows the principle behind the oil bath designs that made these windmills self-lubricating. The main casting here doubles as an oil reservoir, and on an 8-foot mill like this one, that casting held about 2 quarts of lightweight oil. As the pump rod goes up and down, a ring on the Pitman guide picks up oil from the surface of one of these gears and delivers it to the upper working parts. A sheet metal hood covers all of the working parts to keep out the elements.
All of the oil bath style air motor windmills govern in the same way. An off-center wheel automatically turns away from increasing winds, placing tension on a coil governor spring connecting the tail with the head. Then as the wind velocities decrease, this spring pulls the wheel back to face the wind more squarely. The self-oiling air motor windmill is the most common windmill used in the world today. The factory in San Angelo, Texas, builds the latest 802 model. Manufacturing begins at a large foundry in Oklahoma, where the cast iron gearbox is made. Sand is packed around wooden forms, which are later removed, leaving a sand mold shaped just like the gearbox. Iron is melted in furnaces, then poured into sand molds. When the liquid iron cools, the molds are broken apart and the rough casting removed. These rough castings are then shipped to the factory, where they are carefully machined. All of the various components of the gearbox are produced in lathes run by a machinist. Even the gears are made here with machines called hobbing lathes. Various components are sawed, then bolt holes are punched in large punch presses. The gearbox is covered with a metal waterproof helmet. These are made from flat sheet metal, which is hand-formed in brake presses. The operator bends the metal to form an open cap, which is then soldered to make it watertight. Every windmill has its own properly sized tail, which can be quite large. These are made individually from plated sheets of steel. Each windmill has 18 blades which make up the wheel. Flat sheet metal is sheared to the proper size, then is bent into the curve shape that Thomas Perry designed over 100 years ago. The curved and punch blades are assembled into 3 blade sections and shipped to a galvanizing plant. Galvanizing is a hot dip process that coats the blades with zinc. This zinc plating protects the metal from rusting in any kinds of weather. When all the various components have been fabricated, the gearbox can be assembled. Finished windmills are then crated and are ready for shipment around the world.
Not every windmill looked like the ones common today, or even did the things that they do now.
One of the most striking of the historic wind machines was the twin-wheel windmill manufactured in Hutchinson, Kansas during the teens and 20s of the 20th century. Instead of having a single wind wheel, these striking machines had 2 large wheels side by side. They were designed to pump large volumes of water for irrigation. This one elevated water to irrigate an alfalfa field just south of the town of Canyon in the Texas Panhandle. It stood there for many years, but now is gone. The crowd gathered here near Hobbs, New Mexico almost a century ago was amazed when the Kansas-built twin-wheel windmill pumped its well dry in a matter of hours.
Let's climb to the top of the last remaining twin wheel and see how these fascinating machines worked.
This is an exciting place to be on a windy day, but it was dangerous to work on these big double mills. There's no service platform to stand on. There are no brakes. If you want to stop the mills from turning, you have to climb up here and balance yourself on the ironwork while you catch the 2 wheels and tie them together with a chain. A precarious task, to say the least. Let's watch what happens when Ryan, down on the ground, turns his big mill on. Okay, Ryan, turn it on. Look how the wheels are counter-rotating. They capture the free power of the wind and transmit it through gearboxes set at each end of the mainframe. Large drive shafts take that power to the center of the head. There, the ironwork converts it into a usable pump stroke. You have 1 tower, 1 well, 1 sucker rod, driven by 2 12-foot diameter steel wheels. And it pumped a lot of water too. On this well, over 50 gallons a minute. Not all windmills, however, pump water.
From the 1850s onward, makers designed and produced factory-made windmills to drive feed grinders, industrial machinery, wood saws, lathes, and even churns. These mills converted the rotary motion of the wind wheels into spinning steel shafts that operated machinery. The companies called them power windmills to distinguish them from their water pumping mills. Users erected their power windmills on top of blacksmith shops, livery stables, and barns for grinding flour and meal and running machine shops. One happy customer about 1892 wrote to the maker of his power mill.
It is now grinding all the feed for 6 horses, 24 head of cattle and hogs, shells all the corn, and saws all of our wood. It does all the churning every day, and finally runs a pipe organ so the girls can have a song and a dance while the machine is doing their work.
One of the most popular of the power windmills was the Power Air Motor, made by the Air Motor Company in Chicago. Introduced in the 1890s, they remained available into the 1920s.
This is a Power Air Motor made in early 1900. 12-foot steel wheel drives a set of open gears, which in turn drives a drive shaft. This rotating shaft extends from the mill all the way through the building to the floor below. The rest of the windmill operates like a regular water pumping air motor with its offset wheel and hinged tail. Since it's turning, let's go down and grind some corn. The drive shaft is connected to a corn grinder. This is a very noisy machine, but it will still grind up a bushel of corn in about 6 minutes. That's a lot of cornmeal, all from a windmill.
Some of the most creative and unusual windmills were not purchased from a factory.
Homemade windmills like these became common sights during the Great Depression of the 1930s. They were both clever and cheap. Generally, they used recycled materials like cut-in-half steel drums and the differential from a wrecked car or truck.
Truman Chandler built this one outside Merced, California, about 1941. All over North America, people built their own windmills. E.H. Vedetto constructed this merry-go-round style machine in the 1890s near Lincoln, Nebraska. At the same time, J.S. Peckham constructed these big multi-bladed battle axe style windmills to irrigate his orchard near Gothenburg, Nebraska. J.S. Brown saved money building his own windmill. He reported that it cost him a total of only $1.50. None of these homemade windmills were built for beauty. Instead, they built them to use the wind to do human work, and this they all did. Sometimes the problem was not how to build a windmill, but rather how to put one up.
This is a situation that Ted Russell found himself in on his farm near Vega, Texas about 1920. He was able to get himself an oil bath air motor windmill, but he could not afford to build a new tower. He put his hands on some cast-off oil field pipe and from it fabricated this tower that for years supported the mill while it pumped water for his family and animals.
Many people in countries overseas used windmills manufactured in the United States. At least as early as the 1860s, stateside makers began exporting their wind machines around the world. A globetrotter in the early 20th century might see, for example, a Dandy windmill from Illinois and Mozambique, a Samson also from Illinois and Morocco, or an air motor pumping water for a seaside resort in Cuba, or an Indiana-made steel star pumping mill for a water slide amusement attraction in Nantes, France. Perhaps the greatest concentration of exported American-made windmills was in Mexico. People living in some regions used them by the thousands. Another of the important countries for the manufacture of windmills is South Africa. For years, Southern Africa imported windmills from America and Europe, but in the middle of the 20th century, its own windmill manufacturing industry sprang up.
The most prominent of the South African makers today is Southern Cross, a company that traces its origins to Australia in the 1870s. The company makes a wide range of water pumping wind machines, from 8 feet in diameter to this huge 25-footer. We're at the top of a 55-foot tall steel tower at the head of the big Southern Cross mill. You can see that it dwarfs any human that comes up here. The direct stroke pumping mechanism is housed here, and it provides one stroke of the pump for each revolution of the wheel. There are no brakes on these big machines, so any service work has to be done carefully. The worker rides the head as it orients into the wind.
The world changed with the introduction of electricity. By the 1880s, cities in the United States began to have electricity generating stations that furnish current to illuminate homes and workplaces. In 1887, Charles Brush of Cleveland, Ohio, erected a huge experimental wind generator behind his mansion in the city. Brush was the first person in the world to successfully generate electricity on a tangible scale using wind power. His installation was mammoth. The 60-foot enclosed post-mounted tower had a 56-foot diameter wind wheel comprised of 144 wooden blades. Inside the tower, he designed and installed a dynamo that could generate 12,000 watts of direct current electricity. In 1893, the Lewis Electric Company of New York City offered the first commercial wind generation system in America. Years passed before ordinary consumers could purchase wind generators for use at their homes, farms, or ranches. One of these was the Woodman's Manufacturing Company with its Fritchley wind generators, and the Perkins Corporation with its Perkins Air Electric, and the Air Motor Company of Chicago with its electric air motor. The development of small wind generators like the wind charger stemmed from an increased understanding of airfoils and propellers that resulted from aviation. These new ideas led wind power experimenters to try aircraft-style propellers on their wind generators.
This is one of the small home-sized wind generators that came onto the market between 1920 and 1930. Zenith Radio Company sold these small units as a means to promote sales of radios. The single wooden blade is a true airfoil, so it spins quite rapidly. Speed control was the big problem for wind chargers, as blades were not adjustable. The company installed what they called an air brake to help slow down the prop in a high wind. As the wheel spins, it turns an electric generator located in the head of the machine. Electricity produced there moves by wires to batteries at a lower level. The wind machine charges these batteries, which then furnish power to illuminate buildings, power radios, or some other service.
Near the beginning of the new century, large modern wind machines called wind turbines are being used to generate electricity on a massive scale. Erected in groups of as many as 200 generators, these clusters are called wind farms. Today, many cities across the country receive at least a small percentage of their electric power from wind generation, even though the wind turbines may be hundreds of miles away.
A new wind turbine has just been erected at the museum. Let's see how it was done. We first have to find out if there's enough wind to justify the purchase. This wind anemometer will record the wind speed over a full year. If the winds average 14 miles per hour, that's enough to begin construction.
To hold up a big wind turbine, a massive foundation is needed. A hole 26 feet deep and 15 feet in diameter is dug in the hard earth. To keep the sides from caving in, the hole is lined with a corrugated steel cylinder. Anchor bolts, almost 1 1/2 inches in diameter and 26 feet long, are strung into the hole. A steel centering plate is used to evenly space the anchors. All 80 bolts are lifted up so that a second steel ring can be firmly bolted at the bottom. Then the cage of anchor bolts is lowered back down into position. A second, smaller diameter steel cylinder is positioned in the hole. To stabilize this inner steel sleeve, most of the excavated dirt is dumped back in, forming an earthen core. Concrete can now be poured between the two cylinders enclosing the anchor bolts. Over 160 cubic yards of concrete are used. After the concrete hardens, the upper steel ring is removed, leaving a hard, thick concrete base for the new turbine and its tower. The wind turbine is shipped to the United States from Denmark to the port in Houston. A special, extra-long truck is used to transport the turbine blades all the way through Texas. The truck arrives at the museum in Lubbock and just squeezes through the main gates. A 164-foot tall tower, which is made in North Dakota, has already arrived. The bottom half is lifted up, placed over the anchor bolts, and bolted down tight. Then the upper section is raised and secured to the lower half of the tower. The generator and gearbox are housed in a large steel box called a nacelle. It weighs over 46,000 pounds and is placed at the very top of the tower. The wind turbine has 3 carbon fiberglass blades which are bolted to a large hub. Each blade is 77 feet long, and when they are assembled, the wind turbine's wheel measures 155 feet in diameter. With 2 cranes, the wheel is lifted straight up from the ground, turned, and bolted in place. Electric cables are buried between the turbine and the museum building. All of the mechanical components and the computer controls are carefully tested before the turbine is turned on and begins to generate power. Workmen climb the tall ladder inside the tower and carefully check all the mechanical components both inside and on top of the nacelle. This wind turbine will generate over 1 million kilowatt hours of electricity. It will completely power the museum facility, and all the excess electricity will be sold to the local utility. There are no batteries used on this modern wind machine. It is a cost-effective way to generate clean electrical energy from an unlimited power source, the wind.
As we look down from the new wind generator, an air motor windmill near its base still pumps groundwater for cattle. It provides us with a tangible link from the present all the way back to those windmill pioneers of the old world who gave us the concept of using the wind to help do human work.